All right, so good morning, everyone. This is Sandeep Giri. I'll be the instructor for this class for the Big Data and Hadoop course. And welcome to No Big Data. And we would be providing you lifetime access to the content and the class recordings as well as all the material required for learning. As well as we'll providing you the access to the cloud labs. All right. If you have any doubts about any of the things, feel free to drop me an email. And also, please become the active on the forum. All right. There is a forum www.nobigdata.com/forum. And on the website itself, you will see the link. All right. About myself, there are few people who do not know me. So I've been working into big data domain for most of my life. And now I have started nobigdata.com in order to you know help people learn what is big data and what the various tools. All right, all right. So till now we have discussed in the previous session we have discussed what is big data and what is the architecture of HDFS. Okay, HDFS architecture makes it possible to store humongous set of files of humongous size on multiple computers without end user or a developer knowing about the details. All right. So files are distributed across the network. Files are sliced into small pieces and distributed. These pieces are replicated in the network. All right. So that is sort of a summary of what we have discussed so far. Great. Great. So we have 18 members out of 21 who have enrolled. All right. All right. Now, so is everybody clear about HDFS? So HDFS is that file system is the basis of the whole of the ecosystem. And so you'll be asking all your questions by typing and I'll be answering by voice. All right. So any questions till now? Should I carry on? All right. All right. Great. Karthikeyan, you can write to all the people. Okay. Nothing to worry. Hey Ankush, welcome to the session. And okay. Today we are going to discuss something called compute engine. In previous sessions, we talked about what is HDFS and how to store the data. But when it comes to the computation, how to distribute that computation onto multiple computers. That is what we are going to discuss today. Then we take a deep dive into MapReduce and we'll try to understand it. All right. So before I proceed further, let me ask you a simple question. Just to know that how well, I mean, how much aware are you, just to tease you a bit, that if you are given a 1 terabyte of data and a normal computer, how much time do you think it will take to sort it? Sort meaning order the data by lexical order in ascending or descending, whatever you prefer. So you have 1 terabyte of data, about 10 billion names having 100 characters each. Okay. Any other answers than 5 hours? So our sessions, you have to get involved a little bit. You have to interact. You have to ask a lot of questions. So please, even if your answer is absolutely wrong, okay, do not hesitate to answer. Yep. So we are talking about one computer which has 1 gigahertz processor, and just for argument's sake, let's imagine for time being that your hard disk, your data which is stored is on a solid state hard drive. Okay. Okay. So Ajit's point is, are folks using a benchmark to calculate how much 10 billion names? Yep. Okay. So the best sort method, P. Malikram, in case you do not know much about, since we do not know much about this data, we cannot optimize it beyond n log n. N log n is n number of record will take time to process, will be proportional to n into logarithm of n. Okay. So if n becomes doubled, or n becomes say 4 times, then the total number of processing will become 4 times. More than 4 times, actually, not 4 times, more than 4 times. All right. And yes, it does depend on sort method, but not too much. So just give me a rough idea. So P. Malikram says 10 hours closely. That's also okay. All right. All right. So for me, it took around 5 hours, but 10 hours is also okay. A slight bit difference in hardware will take 5 hours to 10 hours very easily. Okay. If your hard disk is slower or your RAM is slower a little bit, 5 hours to 10 hours is not much of a, I mean, it's quite possible. All right. So here, what I wanted to understand is that ordering the data takes time. Ordering the data takes time, inevitably. There is a point from which you cannot take it beyond. I could not take it beyond 5 hours no matter what I did. All right. Now, so, but occasionally, and in industry, when you are dealing with big data, you would need faster sorting, right? And as I said, that I could not take it, and most of the scientists cannot take it, and theoretically it's not possible to take it beyond this time. Okay. So we require faster sorting in industry when we have a requirement of, I'll tell you where is sorting used. Okay. And we would require sorting of bigger data than 1 terabyte. When we talk about petabytes of data, we mean it. And the third problem with this situation is that we would require to do it more often. Okay. More often, as in, every 2 hours, for example. So that means our current solution will not definitely suffice. Okay. And why are we sorting why are we talking about sorting in first place? Okay. Because sorting is probably the mother of most computing problems. Sorting or ordering the data is the mother of most computing problems. Okay. So for example, when we say indexing under the hood is essentially sorting the data. When we say we are indexing a column, it means all the values of our column are taken and sorted, and an index is created. Okay. So that the way you can imagine that behind the book, you see the index, that is what essentially a sorted list of all the words, right? So indexing in case of a database is basically a sorting problem, right? Now imagine this: if you have data of 1 terabyte and you are trying to sort it, and if it takes 5 hours, it will not be acceptable to you. All right. Second, when you do when you do a query on a table, select star from my table, then where where clause basically queries the indexes mostly, and therefore where clause or select query with the where clause is generally an indexing problem. Okay, and hence a sorting problem. Second, group by in case of a select query is essentially a group by of a select query is actually a sorting problem, because when you say group by, what does it do? It sorts all the values, then traverse from the top, whatever values are same, it groups them together, right? So effectively, group by is nothing but a sorting problem. Similar is the case with when we join two tables. Okay. When we join two tables, table A and table B, and we are joining them on the basis of two columns. Okay. So, so when we are joining these two tables based on two columns, the best way to join them is sort this data by these columns on which we are joining, and then it's quite easy to traverse and then match the two places, right? So joining the two tables is effectively a sorting problem, right? And you can come up with more use cases. Order by is blatantly a sorting problem. So what I'm trying to portray is, though sorting sounds like very algorithm or data structure thing, but it is the mother of all the problems do you see in case of data churning. Although there are many such problems which directly are not related to sorting, but part of those problems get simplified with sorting. For example, searching on a map. Okay, searching on a map directly is not a sorting problem, but under the hood, under the hood, it is essentially solved using partly sorting the data. Okay, so here what I'm trying to prove and what I'm trying to pitch is sorting is the problem to solve, and probably easier problem to solve when it comes to the computing. Okay, because sorting is something on which the people have been working for maybe hundreds of years, since the time they started shuffling the cards and trying to create the libraries. So sorting problem is being discussed and solved, and there are hundreds and thousands of algorithms of sorting. Okay, and also there is something called sorting benchmarks industry wide. So all these companies, big shots, come and compete on the sorting benchmarks and prove that they are better at sorting. Okay, couple of times Hadoop has won that A couple of times Hadoop has won that competition, and last time Google won it. I mean, in 2011 they were able to sort 10 petabyte of data using 8,000 computers. All right. Now, so can we do sorting on multiple computers? Can we do sorting on multiple computers? That is the whole idea about MapReduce of Hadoop. All right. Now let's move ahead a bit. So the second section of the diagram which we displayed earlier, the lower portion is HDFS, and you can see that the upper portion, which is a MapReduce engine, now we call it Yarn engine, YARN. Okay, and that is still used interchangeably. Okay, is similar to what our HDFS cluster was. Now, in case of MapReduce engine, we have got a job tracker, sort of the master, and task trackers. Task tracker 1, 2, 3, 4. All right. So whenever we want something to be accomplished, we ask job tracker to do the job. Okay. The client asks job tracker to do the job. Job tracker talks to the name node and asks for where is the file. Okay, so whenever we ask job tracker, okay, so let me go step by step. So first one is the job tracker is the master guy who is like a supervisor on the floor who does nothing but delegate. Okay, so whenever we are asking job tracker, can you sort this file or can we do this, it basically delegates to all the task trackers parallelly and does the job. All right, and in case and it returns the result only when all task trackers finish. Okay, in case one task tracker is taking too much of time or has failed to respond to the heartbeats which job tracker sends to the task trackers, then job tracker will assign the same work to somebody else. All right, is everybody with me on the job tracker task tracker thing? All right, so basically the client, yes, the heartbeat will be sent from task trackers to job tracker, and task tracker will also keep on updating its status by the way of the the job cards. I'll describe that. Don't worry. So all the clients ask to the job tracker to do some work, it delegates to the task trackers. Okay. Now the detailed diagram goes like this: the user submits the job. That's basically you. Okay, before that, before moving on to that, so here there is one more thing. As you can see in this diagram, as you can see in this diagram, task trackers are generally located near to the data nodes. And when you are building your cluster, these are various processes running on your cluster. And when you're building your cluster, when you're building your cluster, you basically keep task tracker and data nodes on the same machine. What does it mean? Your files are closely located with task trackers. So first portion of file 1 is on data node 1, which is closer to task tracker. Second portion of the file 1 is located on data node 2 and which is located near to the task tracker. All right. Now whenever we want processing, we tell that this is my data. This is my file I want to process. Okay. And job tracker will find out. where on what all data nodes. So first step is it will find out on what all data nodes this file is located. Okay, on what all data nodes this file is located. And once it has figured that out, it will find what all task trackers are running nearby nearby those blocks of file, right? So we solved two problems here. First, we divided the work amongst multiple computers instead of getting it done from one. Second, we send our code, the whatever work we are sending to task tracker, right? And task tracker is located near the data. So we avoided transfer of the data. Instead, we transferred our logic. Okay. So this basically makes sure that, because when we talk about big data is in terabytes, and your code cannot go beyond few MBs, no matter how brilliant, you know, how big is your team, your code cannot go beyond few MBs. Okay. So therefore, it is always safe to send the code to the data instead of bringing data to the code. And that's what the whole, I mean, the whole Hadoop MapReduce compute engine is about. Okay. So quick question for by Sanjay. Job tracker will get the info regarding data through name node. Yes. So job tracker queries the name node asking, hey, where is this file located? And name node tells that it is located on node 1, 2, and 3. And then job tracker figures out that what are the task trackers closer to this data node. All right. And this distance, a quick question, is heartbeat interval and failure tolerance configurable? Yes. Okay. So Apu's question is very, all right, good. So is coupling between task tracker and data node tight? Task tracker can use only data node A. The answer is no, right? There are few reasons to it. First, one block of file can exist on multiple computers. Okay? So in case one particular data node is busy, or one particular task tracker is busy, so the work can be sent to another task tracker having the next block, right? Now, question about data node and task tracker. See, imagine this, that there is no task tracker. There could be a scenario where there is no task tracker running on a data node. You realize that this particular computer has got really really bad CPU, as in it has got less CPU cycles, right? So in those, but it has got a big hard drives attached. In those cases, what you will do is you'll keep task tracker on a different computer, or maybe that particular data node is so busy. I mean, task tracker on the machine on which the data node is there is so busy that you cannot give it any work. In those cases, the task tracker, which is very nearby that data node, not necessarily on the same data node, nearby the data node, will get the work. And there will be this transfer which will happen, that network transfer between the data node and task tracker will happen. Okay. So it is just that the overall idea is to minimize the total traffic, total network traffic. Okay. Are there backups maintained for data node? Yes, yes. So backup, there is no need of having the backup of mirror image of any data node, because the blocks located on the data node are anyway replicated. Okay. So there is no backup of the data node. Instead, the backup is of the blocks of the file located on the data node. Okay, good point. Abu's point is that nearby in what terms? So when we when we execute, when we configure our Hadoop, the distance is by default computed based on the IP addresses. Okay, we call it locality optimization. So for example, if there are two IP addresses in which only the last number varies, and there is another IP addresses in which the second part of the IP address, last part, there are four parts to an IP address, right? Like for example, 192.168.1.2. Okay, so in case there are two IP addresses which differ in only the so there are, let's say that there are A, B, and C IP addresses, and let's say there are three IP addresses: A 192.168.1.1, B B this one, and C this one. Okay. Now, which do you think are closest, A and B, or B and C, or C and A? Can somebody tell me quickly? A and B are closest to each other. Perfect. Perfect. Why? Because only the last number is changing. That is what Hadoop also uses it. Right? On the same line, if you have D and its IP address is 4, so the distance between A and B is equal to A and D and equal to B and D. Okay? That is something. Okay? And let's say A1, here the distance between A1 and A is 0. Okay? A1 and A is lesser than what any of this. Okay, because they are all located on the same computer. Is clear to you, Apurv? Unlike other systems, there are multiple ways to do this kind of distance computation. One way is by doing pings between the network computers, by doing, pinging. Let's imagine for time being that each task tracker would ping all the data nodes and compute how much time it took for the ping to return. Okay, and based on ping is sending one unit of packet and noting down times. All right, so let's imagine that what if Hadoop did this way, that each task tracker will ping all the data nodes and find out which one is the closest and tie it, right? And keep a record of which one is closest, right? But this way there are multiple problems associated with it. First, it it basically increases our ping traffic in the network. Second, pings might lie. Pings might lie, and therefore they will not be true representative of whatever network is about. Okay. So instead of guessing, it takes a configurable value. By default, it takes care of does it based on IP address. Later point of time, you can also configure it. I'll talk about configuring it later point of time. So task tracker knows that which are the closest node to it. There's the order of preference in which it will talk to the data nodes, and name node would know that which data is lying on which data nodes. Okay, so job tracker. All right, did I miss anybody's question? Task tracker can also use the duplicate to read from different data. Yes, yes. Okay, so probably. All right. Yes, metadata information is located on the name node related to which data is where. Okay, you say you have a big file, one part, name node will know all of this. So the flow looks like this when we talk about computation. User will talk to, first of all, whatever data user want to process, user will copy that data to the file system, okay, HDFS. And once user has done it, user will create a job and submit it to the client. Now client will, Hadoop client, that command line one, Hadoop client will get the input files info, okay, from the Hadoop file system, right? So the client is the guy who is doing all of your job. Client is the user's representative, okay? So Hadoop client, which does all the hard work for the end user, you are the user. You copied the data. Now you ask the client, can you get my work done? Now this client command line will first get the information about the file, and when you submit the job, you as in yourself will show it. When you submit the job, you tell that this is my logic which needs to be executed on all machine, and this is a file which I want to process. All right, now this client, the command line, will gather information from the file system and accordingly create the splits. Okay, these are called input splits, which data is being fed to which logic. Okay, and after this it submits the job to the job tracker. Is name node then the single point of failure? Yes, the name node looks like a single point of failure, but most of the time name node keeps on delegating the work to others, as well as we maintain the backup of the name node in two forms: secondary name node as well as backup name node. Alright. We will talk about creating splits, okay, Malik, because creating splits is little bit a tricky game, because as we talked about earlier, the file when sliced by HDFS into the sizes of 128 MB is little ruthless. As in, if you are doing a computation on word by word, so by HDFS, half of the word might be on one of the block and rest other half would be on another. So to do that rebalancing, input splits are created. We'll talk about it in detail. Right now, let's talk about this. And client also, after creating the splits, client also uploads the job onto the Hadoop file system and then gives the work to the job tracker. Now, the next step is the job tracker guy, this guy. So we pass the file name reference while, yes, we always, when we are processing the file, we always tell Hadoop that we want to process this file. Okay, or multiple files or a folder. Yes, you are right. Good. So if your processing requires a folder or hundreds of files together, you pass all those list of files to Hadoop. Okay, to Hadoop client, so that it can figure out what to do. Right now, once it is done, the next step after submitting the job is initialize a job queue. Okay, just like on the shop floor, the supervisor creates a queue of work, or you can imagine when the waiter takes your order, it puts it in the queue. It is a physical sort of a box where it puts that card, job card, and the chef takes it and prepares it and puts it back there, and signifying that this job is ready and the food is here, right? Similarly, job tracker initializes a queue, and in queue it tells that, hey, this work is being delegated to this guy, this work is being delegated to this guy, and all of the job queue per task tracker is created over here. How many of maps and reduces whatever are being created, that is mentioned here. Once that work is done, now, so as you can see that we have created something called maps and reduce. Don't panic as of now, okay? And don't worry about input splits. As we go along, there are 4 sessions in which we cover map reduce. We will explain each and everything, right? And afterwards, job tracker keeps on sending heartbeats to all the task trackers. Okay, it keeps on sending heartbeat, as you can see. The or task tracker keeps on pinging back and forth saying, I'm working, and the moment it doesn't receive any heartbeat from task tracker, it just drops that work. So let's say there were these 5 job cards, and these job cards were given to these people. Okay, now in case a particular data fails, that work will be located to any other machine. Okay, we'll go about it a little more in detail. So this is my job queue. Job queue we have the details about the first task has gone to first task tracker, second task has gone to second task tracker, and so on. And in the meantime, it keeps pinging, or it keeps receiving pings from all the task trackers that, hey, I am alive, I am alive. I- okay, and once all of these task trackers finish their work, the whole job queue is finished, it returns to the end user. Okay, so the essence of this discussion is that job tracker delegates work to the task trackers, specifically those task trackers which are located near the data. Okay, in case one task tracker is busy, the one which is closest to the data is busy, it is sent to the next one, which is next closest task tracker to the data. Okay, are job tracker, task tracker both multi-threaded? Yes, but there is no need of having those multi-threaded per se. All right, there is no need of having it multi-threaded, but you can write your logic. If you are writing a Java program to be run as job tracker, task tracker, you will create your own threads inside each of them. Okay, so job tracker, when it's executing your work, it does threading to a very large extent. Otherwise it will not be able to do multiple things parallelly, but it will be creating only single process for you, a single thread for you. Okay, if it is going to work on somebody else's work, it will create another thread for them. Okay, and per job it will create one thread. All right, you can create under your code, you can create multiple threads. Okay, now, so this is the general flow of what happens at job tracker, task tracker level. And as we go forward, we will go into the details of every part. How is the data locality optimization happening? Meaning, how does it really compute the distance? How are other optimizations taken into account? And how is the map reduce happen? Okay, so take a step further. Let's take a step further. So now, just now we talked general about this is how it divides the work. But what exactly is MapReduce paradigm? What exactly is MapReduce paradigm? Okay. So to divide, the biggest challenge starts when you try to divide your work onto multiple computers. When you try to divide your work on multiple computers, the whole complexity starts. There are, when you think about it, you will realize that most of the work, the way we work, the way we code, the way we do computation is not really parallelizable. It's not really that it can be distributed so easily. Therefore, therefore you need to think in terms of different paradigms. Okay. Say for example, when we do for loop and we are doing for let's say we are creating we are computing the count word count. Okay. So the way we do is we pick up one word, put it in a hash table, count it, and go forward. So that kind of flow, the way we do the counting of the words, that kind of flow is not really parallelizable. We cannot get your work done by dividing work amongst the various task trackers. Okay. So to facilitate the division of work uniformly across task trackers, as well as to take the real benefit of data locality, to take the real benefit of to take the real benefit of sending code to the data, you need to use a new set of paradigms. One of such paradigms is MapReduce. Okay, MapReduce is nothing but sorting algorithm given to you. Okay, sorting algorithm given to you. Now, first, let me talk about what does it mean by sorting. Okay, so the problem which we threw in the beginning, that you have to sort 1 terabyte of data, can we do it using multiple computers? Okay, so imagine this: there are these three task trackers, task tracker 1, task tracker 2, task tracker 3, and there is one another node, okay, on which further processing will happen. So we want to sort 1 terabyte of data. We found out that one third terabyte is on this machine, one third on this machine, one third on this machine. And we sort all these three datas independently. Okay. We sort these three datas independently. And once we are done sorting those three data, what we do is we merge them. Okay. We merge them. And in merging, basically we we merge it and then sort it. So already the data, the parts are sorted, each one third part is sorted, then it's merged. And merging is essentially very simple task. Okay, merging is essentially very simple task. I'll talk about it a little more. So can somebody tell me quickly, is it easy to merge the sorted queues? So let's say there are three queues in which people are already standing in the order of their heights. Okay, in the increasing order of their heights, there are three queues. Now you want to merge these three queues into a single one. Okay, so how would you merge these three queues into a single one so that the output should also be such that person these people are still in the increasing order of their heights? Perfect, perfect. So all you need to do is you stand in front of all the three queues which are all in which there are these three queues in which people are standing. You are standing in front of them. All these three queues, the one who is at in the beginning of the queue, who is facing towards you, is the shortest one, and the one who is farthest from you is the tallest one. So there are these three queues, like the prayer time, we used to have that. And so, and you want to merge them into one. It's quite easy, right? You take the p persons who are at the head, take the smallest out of all the three, and put him into a fresh new queue. Okay, and then pick up the next, compare the next three, and pick up the shortest one of those three, and then put him just after the one in after the one you just added into the fresh queue, right? So that is what we call it as merge. Okay, that is what we call it as merge. So what we did was we asked, so we had whole class of people and we wanted to form the queues. All we said that the people in the first row should sort amongst themselves. First queue sort amongst themselves, second queue sort amongst themselves, third queue sort amongst themselves, and then we merge them together. That is the easiest way of sorting, or making a queue in the class. That is easiest way to forming a queue in a class where people are standing in increasing order of their heights. All right, is this clear, that dividing the work on multiple computers really solved your problem? So in the same analog with the by the same analogy, all we did was asked each of the task trackers to sort their data. Okay, once they have sorted their data in one go, we merge that data, and all of our data is now sorted. Okay, so part 1 sorted by first task tracker, part 2 sorted by second task tracker, part 3 sorted by third task tracker, and we just merge them to form a huge part which is sorted, right? So this essentially solved two problems. First, there was very less transfer of their data. Second, there was very minimal amount of load which went on the single computer. Only the merging was done by a single computer, while sorting, actual sorting was done by multiple computers parallelly. And as we talked earlier, sorting is an intensive process. Try sorting something, try sorting a pack of cards, you will realize that it is actually a difficult process. Okay? And now, so MapReduce is all about sorting the data. So Hadoop guys wrote a beautiful sorting algorithm which does all of this. Sort this data and then merge it. Now they wanted to give it to you so that you can take the benefit of it. Okay. So how can you take the benefit of it? You tell Hadoop first you tell Hadoop that here is my data and I want to sort it based on this particular key, and Hadoop will sort it for you, give it back to you in the form of key and multiple values. So it will sort and then group it and give it to you. Okay? It will sort and then group all the values for a key and give it to you. And and then it lets you write another function called reduce. Okay, which basically, so map is something which takes the raw data and converts it into sortable things. What does it mean by converting into sortable things? Specifying that please sort my data by this particular key. So each map gives out keys and values, right? On that basis of that keys and values, Hadoop is going to sort your keys and values, and after it has sorted and merged, pass it through your reduce function, this reduce function, and going to give you the output. Won't it be better if we have more merge nodes, something like a binary tree. Very good point. Excellent point, Apur. Yes, we can have multiple merge nodes. Then the system will get little more complicated. We'll talk about it in in a few slides later. Okay, so everybody is convinced that first we tried to break our processing, break our computation onto multiple nodes. Okay, or Hadoop did it for you. Hadoop basically implemented the distributed sorting for you, so that the work is delegated to all the machines, not only the single one. And then it facilitated you so that you can exploit this sorting algorithm. How? You can define that, hey, sort my data. You can define that how to sort your data, and after it has done the sorting, how to how to combine the sorted data. Okay, so that you do in terms of maps and reduces. You define a map which spits out keys and values. On the basis of keys, Hadoop sorts the data, and once it has sorted the data and grouped the data, it will do a reduce for each key. Okay, moving on. So that was about MapReduce. Rest we have taken care already. So all of you have your account on our system already, and you can log in and start working. So let me just pick up the. Oh, we haven't taken a break. Uh, should we? We'll take a break in 30 minutes. Don't worry. We'll take a break in 30 minutes. All right. Any other questions here? I know there are a lot of questions because the map reduce doesn't go that easily. So let me just open the second presentation and start working with the. All right. So all right. So this is okay. This is what we had talked about. Now earlier. So we just talked about distributing computing on multiple computers and then taking the benefit of that distribution by the way of maps and reduces. So there are two things. Earlier these two things were combined together. Map reduce earlier in Hadoop 1.0. Okay. Reduce means reduce will be your function just like aggregate function. When you say group by and then sum, so sum is your reduce while group by key is defining the key for sorting your data. Right? We'll talk about it more and more. When you see more examples of map reduce, you will get it. By the end of today's session, you will get it clearly. All right. So everybody is with me, or there are all right. I think nobody is with me. Okay. Okay. Now, earlier, MapReduce, the sorting thing as well as distribution of work, both were a single unit, which means there was only one way of MapReduce. There was only one way called MapReduce with which you could do the churning. In the Hadoop 2.0, they did a very beautiful thing. It's done by a guy from Hortonworks, and what he did was he splitted MapReduce into two portions: the pure MapReduce, the paradigm of sorting, and the task tracker job tracker. So task tracker job tracker became Yarn, that the way task tracker job trackers work, that became yarn, and MapReduce just became one form of processing. Okay, so that was a nice thing which he did. Because of that, now there are multiple competitors of MapReduce as of today. Okay, now we have, now as you can see, MapReduce was the first one. So yarn basically takes care of how to divide any work, how to divide any work amongst multiple machines. Also taking care of which machines are up, which machines are down, where is your data located. All of those kind of processing was taken care by yarn. Okay, basically yarn means yet another resource negotiator. It negotiates resources with all the task trackers and name nodes and job trackers. It tries to figure out which one is the most suitable candidate for the work to be done, and and how to delegate it and how to collect the result back. That is what is done in yarn, while MapReduce is basically one single paradigm which is based on the sorting. Okay. Now, as you can see that after Hadoop 2.0 came in, lots and lots of other things came in. So at the bottom you can see HDFS, Hadoop file system. At the at just above it there is this task tracker, job tracker kind of paradigm where the work is delegated amongst them. On top of it, MapReduce takes the benefit of yarn. Then Taze uses yarn, and all of these basically uses yarn for dividing their work amongst multiple computers. It's not only MapReduce anymore. Okay, so this is one nice thing that happened, because of which we see a lot of new products coming in, every day. All right, so it's just that this yarn has got too many components that it confuses all of us. Okay, can you please explain the redundant part in HDFS? Redundant part as in, okay, so here they have started calling redundant. Redundant basically means that all of the blocks are replicated onto multiple machines. Therefore, each data node effectively is redundant. So at least one data node always is completely redundant. If there are n data nodes, you can safely turn off one of the data node, and still the whole HDFS will keep on working as such. Right? But if you have a replica factor of only one, then none of your data nodes will be redundant. All right. Now going ahead. Now the same structure, same architecture can be little complicated, where there is a now now basically Yarn supported the workloads other than the MapReduce. Yarn gave you the great scalability. Yarn gave you compatibility with the old MapReduces. The other beautiful thing that happened in Hadoop 2.0 is that all of your previous work, all of your previous MapReduce will keep on running as is without any modification. Just that you had to recompile it once. Okay, because API got a little upgraded, so you had to recompile it. Other than that, so generally what happens is when people do re-architecture or something else, your code which was dependent on those libraries break. But that did not happen in case of Yarn. That was a very nice thing they did. And they also made sure that the cluster is better utilized, few better algorithms for utilizing the resources. Now, job tracker, task tracker became something like a global resource manager, and they were broken into so many components, right? And as you can see in this diagram, so your job tracker essentially is now called resource manager, while the task tracker is actually the node manager, and then there are rest, okay, to facilitate all of this. So it will be easier for us to call job tracker to resource manager and task tracker to node manager, okay. But there's too much of terminology, that is why I keep avoiding this diagram as much as I can, okay. In the essence, at the heart of the whole process, it is resource manager or job tracker which delegates the work to the node manager or task tracker, okay. And all of these other components take care of the resource utilization. All right, so this is what Yarn is about, yet another resource negotiator is about. All right, now before moving forward, let's just go ahead and have a look at our cloud. All right, so here you can see that, first of all, let's have a look at HDFS. Okay, HDFS shows that there is name node is up and secondary name node is down. Data nodes, four data nodes are alive. We are adding one more node to act as a secondary name node. Right now, if our name node dies down, then we'll have no other fallback, right? So this is a dangerous situation to be in. So we'll be starting up either the backup name node most likely, and or secondary name node, either of the two, right? Now, so this is our HDFS. You can see that it shows that there is 93.1 GB available, and let me just go to the dashboard. So total disk space, what it has computed is, I mean, what should I say? So DFS used is 26.2 GB, and remaining is around for 40 GB, not 40 GB. Can see that DFS uses 26.2 GB, which is 21%, and non-DFS is this much used, and remaining is 43.5. Right. So this is, when we say DFS, right? It is basically accumulated over the all of our data nodes space. Okay, this is the space of our data nodes. Okay, since our servers are solid state drive based, they are smaller. The hard disks are smaller in size, but they are far more faster than the normal hard drives. Far more faster, as in 10 times faster than the normal hard drives. So we have chosen to go with the the solid state drives, and we'll be creating a backup of all of it onto the Amazon server. Okay, so we have got HDFS. Now you can see the HDFS, and here also you can see the name node has got this much RAM, and it's okay. And name node is has been up only for 6.5 days. Okay, now next one is Yarn. Yarn is what we have talked about: job tracker, task tracker, the resource locator. It has got something called app timeline server. So out of which node managers, you can see there are three three node managers, and one resource manager. Okay, three node managers and one resource manager. Node managers is equivalent to task tracker. This one is the job tracker. Okay, and in the similar way, you have got MapReduce engine installed. There is nothing you can do here. Now, this is the way you can see the status. You can log into it if you go to your, first of all, go to your my courses. Under that, go to the first session, and here you will see first quiz and then installation instructions. Okay, here you will see the login passwords for this session. These are the login passwords you can see. So so first log in to the 8080 port, where our this is the admin UI which shows what is installed where. And then if you want to operate upon any of these services, you can go to Hadoop 1 dot no big data and 8000. Here, here you will see something called file browser. This is essentially an HDFS. HDFS that looks so complicated when we talk about it, blocks and chunks and this and that. When it is represented to the user, this is how it looks like. It's a it's a clean file system. You can create your own folder over here by doing, you know, new new file or new directory. Generally, you should be creating your own folder here and then operate upon that folder. Okay. Right now we have a common folder of student. Later on we will be creating individual accounts for all of you so that you can have your private space over here. Right now, let you should be exploring what other guys are doing. Also, you should be creating your folders independently. Okay. Do not delete anybody's data. That will be little, you know, will not make people happy. So this is the file browser, the HDFS, and you can upload the data here from your local file system. Okay, and similarly we can change the permissions. All right, so this is how you can interact with file browser. And there are other tools like Hive, Pig, and then you have job browser where you can see what is happening to your job. Okay, and then you have something called Uzi with which you can submit a job. Okay, we'll go into the details later. In case, in case you want to basically install on your own computer, the best way would be to download the virtual machine. First you download a virtual box, then download the virtual machine, and then after installing the virtual box, you load the virtual machine in the virtual box and carry on. Okay, that's also defined over here. Okay, but mostly you will be happy with the basically using our labs. In case you face any problem using our labs, just drop me an email at hadoop@nobigdata.com and get in touch with us at any moment of time. All right, so now we have seen the web interface. The other way you can communicate to our cluster is by using SSH. So we essentially have 4 5 servers: Hadoop 1, Hadoop 2, Hadoop 3, Hadoop 4. You can SSH to our server by student at hadoop1.nobigdata.com. Or in case you are on Windows, you should download Putty. Okay, you should download Putty and install it. and using putty, you give the login as a student and host as Hadoop 1 or Hadoop 2 or Hadoop 3 dot nobigdata.com, and then connect. Okay, you will get a shell on our servers, okay, where you can do anything you want. Now, so I'm in the folder of Hadoop 1. There are Hadoop 2, Hadoop 3, Hadoop 4 as well. Right now I'm in Hadoop 1. And when I say ls, it's a local files, not the HDFS, it's a local file of that machine. If I have to see what is there on HDFS, I'll have to say Hadoop fs minus ls. Okay, so it is equivalent to seeing HDFS in the browser here. 8000, it is equivalent to seeing the files in the browser. Okay, so Hadoop lsfs is that one. Okay, and in case you want to copy the local file of Hadoop 1 onto the HDFS, you can use minus copy from local, and let's say I want to copy ratings.csv into a folder called asgiri with the name of ratings-sg.csv. Okay, so I'm copying from local file system. Local means Hadoop 1's local. I am right now standing inside Hadoop 1. Okay, Hadoop 1 is one of the servers, and this shell is basically running at Hadoop 1. It has taken me to the Hadoop 1 server. Now when I'm running this command, basically I'm copying one file called ratings.csv from local Hadoop 1. Hadoop 1 is the name of this machine, into our HDFS. And in HDFS we have a folder called asgiri. Let's see, where is asgiri? This is my folder, and under that there are some file, but there is no file called ratings.sg.csv. Now if I do that, it'll basically copy my local ratings.csv. Oh, we don't have that there. Let me just say ls, say widgets.java I want to copy. Okay, widgets.java is there on my local file system on this server, widgets.java, and I want to copy this, not jar, java. Okay, let's see what happens. Now we'll have widgets. Let's refresh it. Widgets.java. Okay, so this is the way, this is the command line with which you can copy back and forth between the local file system and HDFS. Similarly, this is the command line. Hadoop is the command line with which you will be executing your logic. Okay, is the main command line. Okay, now the question from Vishnu is, in production environment we will have access via terminal SSH, or do we have access to Ambari and Hue Manager? That absolutely depends on your organization. That really depends on your organization. While, for example, at InMobi I had SSH access to the cluster, while I did not have access to the SSH access to the cluster at Amazon. Amazon has created their own wrappers on top of Hue, and we had to use to that one. Okay. If more than one, then how to watch data on multiple data nodes? Okay. Okay. How many node managers, data manager? Okay. So Hadoop one is just one machine. I'll show you this. I think it's better. I'll show you this. So I have got how many hosts? I've got four hosts: Hadoop 1, Hadoop 2, Hadoop 3, Hadoop 4. Okay. On Hadoop 1, we have installed what? Name node and job tracker. Okay. And one of the data node also I have done on the Hadoop 1. You can see on Hadoop 1 is one machine. Okay. On Hadoop 1, we have installed name node. On Hadoop 1, we have installed resource manager. And on Hadoop 1, we have also installed one data node. This is a bad practice. We'll be removing data node from the machine on which the name node is there. It's not a great practice to have. We just went a little greedy and we did that. Okay. And on Hadoop 2, we have nothing called node manager. We have basically data node. Okay. On Hadoop 2, we have basically data node. We were planning to put up a secondary name node on Hadoop 2, but we have dropped that idea. We are moving it to somewhere else. And on Hadoop 2, there is something called node manager. Node manager is equivalent to task tracker. All right. Node manager. And all right. So this is what it is. And then we have got Hadoop Hadoop 3. Let's see what is there on Hadoop 3. Hadoop 3 only has data node and node manager. And these are just for monitoring reasons. Okay. One region server is there, similar to node manager. We'll talk about region server when we talk about HBase. Okay. Here, similarly, we have on Hadoop 4, we have only data node and node manager. Okay. All right. So we have got, effectively, we have got Hadoop 1. Hadoop 1, we have just given it a name. We could give it name as Cloud Lab 1. Okay, Cloud Lab 1. Okay. So the name of this machine is Hadoop 1, Hadoop 2, Hadoop 3, and Hadoop 4. These are the four nodes we have. And on Hadoop 1, we have put name node, name node, and we'll be moving data nodes from here. And we have put job tracker, aka resource manager. Okay, resource manager. And on Hadoop 2, we have put data node. Hadoop 3 also data node. Hadoop 3 also data node. Okay. And here you can here we have got something called task tracker, and here also task tracker. So basically the main guy out of all of these machines is Hadoop 1. It does mainly the churning. In case you are SSHing onto Hadoop 1, okay, if you are doing SSH on Hadoop 1, you can basically, in case you get that memory goes little above the thing, you can also talk to Hadoop 2, do SSH onto Hadoop 2 or Hadoop 3, and uh, or Hadoop 4, because Hadoop 2, Hadoop 3, Hadoop 4 will, their memory of Hadoop 2, Hadoop 3, Hadoop 4 is small, RAM is smaller. So, but their CPU is mostly busy, okay, because these are the main heavy lifters. If you are doing a lot of processing, then your Hadoop 2, Hadoop 3 will be busy mostly. While RAM of the first one gets full very quickly because name node consumes a lot of RAM. Okay. All right, we have got some questions. Let me go through this. Okay, how do we define authorization or restrictions to the access of document? Thank you. So generally, HDFS provides you, if you, this is a good question. Generally, it provides you exactly similar kind of users and groups the way we have in Windows and Unix. Okay, you can see the permissions over here on each of the files and directory, which says owner can do this, groups can do this, and others can do this. And do this means read, execute, write. So that is what This is how the permissions are taken care. Right now, all of you are sharing a single account called student. From the session 3 onwards, you will have your own separate account. Okay, we are in process of automating and managing these accounts, and till then, you it will be completely okay with all of you that to use the same shared account. Okay, and in an organization you will be basically setting up the separate accounts for individuals and giving them the permissions. Okay, Silpa, was did I make any sense? Okay, so what is the local file system in Hadoop system? There is no, I mean, the local file system is basically the machine on which you are standing while talking to the Hadoop. So Hadoop you installed on some machine, right? So Hadoop is nothing but an application which is running on your machine. So when we talk about Hadoop, Hadoop means job tracker, task tracker, or node, data node or name node. You basically installed all four of these, but either one of the processes you will be running. If you run a process called name node, the machine we start calling that machine called name node. If you run a process on this machine called data node, we start calling it data node. All right, and on the machine on which all of this is running is called local machine. Yes, I mean the Linux is local system only. So right now I'm on Mac. Right now I'm on Mac. I did an SSH. I reached to Hadoop one, which is basically a Linux machine. This is basically a Linux machine, and you can see uname minus a. It shows you that it's a Linux machine. Okay, on which you are running various processes. One of them happens to be Hadoop name node, and so on. All right. Okay. Okay. All right. So the only interconnection between Hadoop 1, Hadoop 2, Hadoop 3, Ajit, is that they're running SDFS files, and name node has been informed that these are your data nodes, and vice versa. Okay. So Ajit, was I able to answer your question? Can you show again just to? Okay. Now, all right. So Abhishek's question is that can Windows also run Hadoop? Yes. Recently, I mean, probably the last this January onwards, I think. I don't remember exactly the date. Probably January or February. They launched something called HD Insights, which is nothing but, although Hadoop was written in Java, it was supposed to run anywhere. But for some reason, the glue code like shell scripts which launch Hadoop were not there for Windows. So people from Hortonworks and Cloudera and Microsoft, they actually built something called HD Insights, which is exactly the same Hadoop with which runs on Windows. Okay. So now somebody was asking me to show the file system again. Oh, it started downloading the file. Right. So Shilpa's question is, do only admins churn the data and generate the report? So basically a technical Hadoop team, is there interface for end user, say management, to see the data themselves? So as of today, the the interface which we are going to talk about is generally the little bit developer oriented. Whether we talk about pig, in which you will be writing SQL kind of query, or the, the hive, in which you will be writing proper SQL. So all those kind of interfaces are available, right? But the management interface for reports and other things is not in this. what people do is they build their own reporting portals that basically connects to hives. So I'll show you this. So this is what our this is what our query interpreter looks like. So we can just start writing our queries here, which will basically get converted into map reduces, and will talk to HDFS and give back the results. Okay. So this is the only the the this is the best that it could you could get here in using these interfaces. But lots of people are working on the kind of reporting portals which connect to these systems. And moreover, because all of these systems come with a JDBC kind of interface, so your existing reporting portals can basically directly connect to Hive or Hadoop and get their work done. Okay. Okay. Now, right? Was I able to answer, Shilpa? Okay. So Manish is saying, so I can run ls. Yes, yes, you can run ls make dir commands and create your own directory in the local as well as in the HDFS, and try copying data back and forth, and so that make yourself at home with respect to this Linux command. Okay. As well as HDFS. So how much processing power, memory, hard disk drive someone needs for desktop to run HDFS? So it's not required. It doesn't require much. Okay, it doesn't require much because the only thing you will feel a challenge in is in the RAM. So have at least 4 GB of RAM in case you are trying to install virtual machine. Okay. In case you are trying to install virtual machine, only then you will require to upgrade your RAM to at least 4 GB, because virtual machine consumes a lot of CPU and RAM. That should be good enough for you to use any of the virtual machines. And in my opinion, I found Hortonworks virtual machine little better than the Cloudera ones. So you can try that out also. Okay. Yes, we'll be providing the command reference. Don't worry. All right. Great. Now, all right. So name node, data node, we have Ambari, which we showed you, the manages servers, and Hue interacts with services. And also there are very nice features here. If you are planning to set up your own cluster, this is a good way to do it. So you can basically take any services. So you can take, so say for example, you are here and you're running node managers here, not node managers, let's say resource manager. Okay. So it provides you something like a resource manager, and you can say move. So now what it will do is it will move the resource manager from one machine to another. Okay. All right. Now Hue you can interact with the way we had shown you the file browser, and you can also see what is running on the server and all of that, what jobs are running. Now on Windows, download PuTTY as well as WinSCP. WinSCP is used for copying files and PuTTY is used to connect to the servers. Okay, because lot of things you will require a command line to operate. Therefore, it's safe to have PuTTY at hand. Now you can do you can also on a Windows machine you will already have SCP installed. Sorry, on Linux machines you will already have SCP installed on Mac or SCP. So you can directly do SCP without having to install anything, right? So using web interface, try to create your own folder, and using command line also try to copy a file from local to a folder. Okay. So this is not required right now. Okay. We will talk about it later. All right. As a general quick way, this is how you can basically copy. This not required. You don't need to upload MapRed jar. Okay. So to run a MapReduce command, all you need to do is run this way. Hadoop jar and then the jar file. Jar file is like DLL or the bundle of all the code. So Apu, if the password is available in the installation document, I will not be able to speak here that password because the video might get shared with other people. Okay. Even the screens I've shown, I'll have to delete those frames which contain the password. Okay. All right. So this is basically running a word count. Okay. And as you can see, what we did in this, so it has basically executed it and has completed the job. Okay. So let me show you a little bit about this. What we have said is Hadoop jar execute this jar, and out of this execute a program called word count. There will be multiple programs in this jar. Execute my word count, and this word count accepts one input folder and this output folder. Okay. So Malik, you don't have to put http colon slash slash when you're connecting via SSH. And the port is not 8000. 8000 port is only for Hue. Okay, you only have to do SSH student at hadoop1.nobigdata.com, right? And to see a file, you can see the output for. Okay, so where did it store user student as Giri? So we have just hurriedly tried to execute one MapReduce command using Hadoop command line and execute, get the results. Okay. So basically we were trying to do a map, the word count on using Hadoop, and this is how you see the file using command line. Also same thing you can do from the browser as well. If you go to the file system, so you have got user asgiri word count output, there is asgiri, and then there is word count, there is output 4. This is where the output is generated. Okay. All right. So this is a very quick overview of what happens. Now, before we start thinking in terms of MapReduce, let's take a quick break of 10 minutes and back by 8:42, 8:52. So we will take a 10 minutes break and come back by 8:53. All right. Hi. So, all right. All right. So, should we start now? Is everybody back? Great. So, Vinay is back. Is everybody back? Or great, great. Cool. Then we should start now. All right. So, till now we discussed about how does the file system work, Hadoop file system, and how does the compute engine overall works. And we also briefly discussed about MapReduce paradigm, where how do we exploit sorting to solve our problems. Okay, and as we quickly discussed that most of the problems can be converted into MapReduce, so we'll go deep down now into how to convert most of the problems into MapReduce. Okay, so we'll take couple of examples and go step by step and try to solve those problems in terms of MapReduce. So we need to start thinking in terms of MapReduce before being able to take the full advantage of distributed computing. Okay, so MapReduce is a very important concept, and whether it's Hive or Pig, Hive is SQL interface, Hive or Pig or other components, they all convert their work into MapReduce. Similarly, the newer framework, which seem to be competitor of MapReduce, they themselves also use a paradigm similar to MapReduce, very close. Okay, so it is very important to understand the whole idea of MapReduce. So here first we will try to do solve problems without using MapReduce, using your general strategies. Even if you have never done the programming, try to work with it with us. And in case, y- I mean, I will try my best to make the problem really, really simple. Okay. So So let's say you have got huge plain text files. You've got huge plain text file. Imagine all the Lord of the Rings books, or maybe all the textbooks of the world. Okay. For now, let's just imagine that you have got Lord of the Rings book in plain text file. Now it's just 1 MB. How do you find the frequencies of words? What does it mean by frequency? How many times a word has occurred in this file? So what are the total words and how many times each word has occurred? That's what we have to find out. If you have to do it today and you know that the data is very small, say 1 MB, what will you do quickly? Just write your approach. I'm not asking for an algorithm. I'm just asking you to count the words in a file. What will be your pseudocode? What will be your, right? So Sanjay is saying count and group by. Very good, very good. Okay. So you will first, Sanjay is saying, I think you are talking about using SQL database. First, convert it into a table such that each row contains one single word, and then you do a count and group by. That's what you are pointing to, Sanjay? Good, good. Now, Harish says use a hash map. Excellent, excellent. And iterate through iterate through and search the word. Okay, that is Malik's question. So Malik is saying pick up a word, find that word in. So Malik, give me a little bit more because I am trying to guess and the one which I'm guessing might be little bad. Give me more pointers. Hash map, Manish is saying hash map with the key as word and value as count. Hash map is basically a data structure which acts like a dictionary, which acts like a dictionary in which we put a word and it gives the value. Okay, the way in the dictionary you just look up for the word and it gives the meaning. Similarly, hash map, for you can attach as well as retrieve the values for a word. Okay, so Manish is saying a dictionary with where you look up by the word and the values you store instead of the meaning of the word you store the count. Okay, so Marik, we are not looking for a particular word, we are saying list down all the words and their frequencies, and that changes the problem. Apurv is saying construct a try. Good, good. So great. Construct an array. Good. With the all words. Right. Right. All right. So most of you have answered well, and here is the answer. So first approach, this approach is great when it, you know, we created a frequency table, hash table, or you can call it like a dictionary. Okay, frequency dic, dictionary. What does it mean by dictionary? Basically, you have got word, and in dictionary you have word and their meanings, right? In here you have word and count how many times a word has come. So you pick up a word from top to bottom, you traverse through this file, then you try to find this word whether it exists in our dictionary or not. If it doesn't, we add that word to the dictionary with count as 1, the value as 1, and then keep on moving. In case the word is found, we pick up the next word and that word exists in our dictionary, that we just increase the counter and keeps on moving. At the end of this whole process, you will have the frequencies of all the words that exist in this file, right? Is everybody okay with this solution? Right. When no more words are left in the file, print the hash table. Now, this works pretty well. This works pretty well. But there are a lot of problems as well. Okay. Do you see any problems? Do you see any problems when your input text changes, increases, or some other problems? If your input size changes from 1 MB to say 10 GB, does this solution still make sense? Right, right. Because here this dictionary in which we are storing each word and the value is actually going to take up lot of space. It is actually going to take up lot of space. All right. Yeah. And also, yes, it will take too much of time because for each word you are going to look up, but that is okay. That is okay for now. Dictionary, time wise, this will be good. This will be fast enough actually. Yeah. All right. So is everybody with me? Or so it will take too much of memory. That is fine. That is the problem. Now, basically, whenever you hit the RAM, so dictionary generally takes 4 times as memory as the actual data. That means if you have got 1 MB, 1 MB file, it will take 4 MB of space in the memory. So that's a general statistics. I'm talking in terms of Python and Java hash tables. All right. Now, so what else can you do? So now let's talk about the second approach, which somebody gave nicely. Uh, okay, and like Sanjay said, I think Sanjay gave that answer. So let's talk about the second approach, which Sanjay talked about. Okay, here the second approach is SQL. Break this whole text into one word per row. Okay, one word per row. All right, and insert it into the table. So you have a huge table which has a single column. Each column contains one word per row in this. Now all you did was select word comma count star from table and group by word. Is this comfortable to everybody? Select word comma count star from table and group by word. Will it give the output? Great, great. So now do you see? So this is the people who are comfortable with Unix will get the answer with SQL will uh, agree with me. Now, third way, if somebody asks me to solve it, is my usual Unix command. Okay. Now this time, what will I do is the way in this approach, instead of forming hash table and looking up, all I did was order grouped by a word, which means sorting by a word, and then did a counting. Okay. Remember this approach. This approach is what is going to be used when we talk about MapReduces. Okay. So everybody understands this approach, this SQL approach number two. Good, good, good. All right. So now the third approach, because I am a person who loves Unix and who does a lot of things, and this is how I generally do stuff. The problem which I was talking about took me 5 hours. Actually, it has a deviation from this approach, was a similar approach. So all I did was first I took all of the text files, put it in a single file. Okay, just put it in a single file, then replaced new line with space. Okay, I replaced space or tabs with new line, such that if you replace tabs or space with a new line, what happens? You will have one word per line. Okay, you will have one word per line. Right now in this big plain text file I have one word per line. Next I did was I sorted this data. Next thing I did was I sorted this data. And good part about the sort command is that it can be told that only take this much of RAM. If I have 1 GB of RAM, only take 1 GB of RAM. I can tell that. So I told sort command to sort the data which I just broken into one word per line. So sort my words, sort this list of words, only consume 1 GB of RAM, and then whatever result I got, I said unique minus C. Unique basically finds the counts of unique words if the data is sorted. So this is another approach. This is another approach. So the difference between first approach and rest of the approaches is first approach relies on creating a hash table, while second and third approach basically rely on sorting the data and then counting it. Okay, and that's what makes the big difference. That's what makes the big difference in these approaches. All right. Now, these second approach and third approach used to work pretty well for most of the time till now. Okay, till the time we had a even bigger problems. So first approach failed when our data started growing to the size of our RAM. Okay, the moment we hit our data size equal to the RAM, our first solution failed. Now, if our data further rises, there is a point that second and third approach might not work. And can you tell me why? What exactly is the problem with second, the SQL approach and unique approach, this Unix approach? So do you see any problems with the second approach and third approach? Anybody? What if there are millions and zillions of word? Okay, right. So what will happen? What will exactly happen? In database, the data log creation, okay, so we can actually turn off the data log creation. We can tell the database to do that. Indexing takes time, good. There are serial operations, good. Time taken to retrieve data is out of temporary space in data, okay. IO, thank you, Abhishek Pandey, that's what I was looking for. Although we all have taken talked about the same thing. Time taken to retrieve data, serial operation. Eh, so basically, after a point of time, when your data grows big, now your RAM is no longer a constraint, but your IO operations, the rate at which you can read write data from the disk and the rate at which your CPU can do the processing becomes the bottleneck. Okay, no matter which algorithm of sorting do you use, you cannot take it any further anymore on a single computer. You cannot go beyond 5 hours to sort that 1 terabyte data, right? Now, we needed a different kind of approaches in this. So, the problems which we see is there are multitude of problems. First, RAM was a problem. Second, hard disk may not have the whole data, so we might have multiple hard disks. Okay, and our disk space, disk speed, CPU, everything becomes the bottleneck as the data keeps growing. Okay, therefore, we require newer kind of approaches. So let's talk about a fourth approach. Okay, a fourth approach is your external sort. External sort, what does it mean by external sort? It utilizes a distributed computing, okay, which means there is a user and user has got two computers. Okay, this user wanted to sort the data, so half of the data is sent to one machine and run one of the algorithms talked about in first approach, second approach, third approach, those either of those three approaches we used on each of these machine 1 and machine 2, and when that work is done, user basically merged the output and did it. So let me repeat again, let me repeat myself. You have two machine, machine 1, machine 2. You wanted to utilize both the machines to do your work, and what you did was you copied half of the data to first machine, half of the data to second machine, and then asked machine 1 or machine 2 to take approach number 1 or 2 or 3, either of the three approaches, where using SQL, Unix command, or using hash table, either of the three commands you ask machine 1 and machine 2 to do your job and give the result back, and then you do the counting, do the merging, and then do the counting, right? So user sent, say for example, our input was sa re re ga ga re. Let's just imagine for reasons, for simplification reasons, that this is the whole text you have. Okay, sa, the first one is first block, second block. You have got a big file containing this one, sa re re ga ga re. Okay, so first three syllables you send it to machine 1, second last three labels you send it to machine 2. Machine 1 did the counting for you. Machine 2 did the counting for you. Once you got the result, you combined them together and gave out the results. And note that Ray went to both machines, this one and this one, and then you had to combine it again. Okay, right? And also to merge these kind of things, the to merge the sorted data, the command Unix command sort gives you minus m uh, operation to merge already sorted data. Okay, that you can use instead of writing your own code. So, are you happy with the approach? Do you see any problems with external sort? Abhishek? This work this will work best when aggregated output is sent, okay? But you cannot do the aggregated output, right? Because so Sanjay's question is how much difference it makes regarding time. It will do the work in around twice as faster. Okay. So do you see any problems with the external sort where we divided the work and get the work done by two machines? Yes, backup of the machine might be required just in case. Thank you, Malik. Yes. So that's right. If you are doing it too frequently, you will have to have the backup of each one. And data transfer. Thank you. So user has to transfer the data to machine 1 as well as to machine 2, right? And that's what will take a lot of time. Okay. So first, data time is consumed in the transport of the data in this approach. And for each requirement, whenever we have to do something, we'll need to code everything. We'll have to write this whole transport mechanism that send this work here, send work there, and all sorts of things. This is a very custom solution. And trust me, it takes a lot of time to get a distributed work, this kind of work to get it right. It takes a lot of effort, right? So therefore, a lot of engineering is required in this solution, as well as the data transfer is quite a headache. So the solution is to use a map reduce kind of approach. All right. Now, what exactly is MapReduce? It's a programming paradigm to help you solve big data problem, specifically the problems which are sorting intensive jobs. You would have to code two functions. One is mapper, other is reducer. Mapper basically converts your input into keys and value pairs. Okay, pairs, note down that word, not pair. And reducer aggregates all values for keys, and then all and MapReduce is not only limited to Hadoop. Lots of products have ended up using giving the MapReduce kind of control in their products. So you can use MapReduce of CouchDB, MongoDB to churn the data lying in those databases. And MapReducers can be written using any programming language, not only Java. Okay? So is everybody with me? So I'll just take you through a example of how do you do a word count on a MapReduce. So you have got a huge text file. All you need to do is form the key value pair such that it is grouped and then you count it, right? So what you do is you write a function. Or we are trying to do right now is write down MapReduce functions for counting the words in a file. So what goes inside your map function? Your map function should convert the plain text file into key value pairs. The key is the one on which the data will get sorted, your values will get sorted. Sorry, keys is the one on which the whole keys is the one which gets sorted, okay, on the basis of which the data will get sorted. So we go through the input. For each of the word in the input, we print out word space 1, word space 1. That's all we print out. Okay. Now, as a result, so imagine that your file has got sa re saga as the input text. Your mapper, this is your function, you will be writing it. This is your job to write such a function. Okay. So your function converts it into key value pairs. Why do we do that? Because we want it to be sorted by keys, which is each word need to come together. Okay. So what we did was we formed the output as key space 1, which is sa1, re1, sa1 and ga1, right? And Hadoop will take this output of your map functions and then sort it and group it. Okay, sort it and group it, and after grouping it will not do anything but form a big array of all the values that belong to a particular key. So sa has come twice, so what is the value for sa? 1 and 1. So it has formed an array of 1 comma 1. Okay, this instead of 1 there could be a huge object over here, right? That object could have come as is. Now the next step that happens, for each of the keys your reduce function will be called, which means for the reduce function you, yeah, right, is it takes two values, one is key, other is array of values. Okay, so for ga and 1, one function called your function called reduce will be called, and sum will be applied onto the values. This is your code which you have written. It's just that Hadoop is making a call to it. Okay, so the result is that when you sum up 1, the output is 1, here also 1, and 1 comma 1, if you sum it up it comes to 2. All right, so basically your map converted your input into sortable stuff. Sortable as in it provided Hadoop that hey, my data needs to be sorted based on this key and group it. So Hadoop grouped it. Later on, you write a function called reduce, and that reduce function basically convert this group of values into a meaningful value. Okay, so you can basically convert lots of problems into multiple combinations of mappers and reducers. So is this clear to everybody? So these two boxes which are there, this is the code written by you. Okay, if you had printed 1 comma word, then all of words could have become a single value, because 1 is the key in that case, right? All of the words could have become the values of this big array, and you could do multiple things, right? And here, in case you want to convert the lowercase into uppercase and you want to take care of those parts also, before printing, convert the, I mean, clean up your word and then print it out. There could be dashes in the input word. Some word could be capitalized, some word could be smaller. There'll be commas which you don't want to print. So all of that cleaning is done in your map function. Okay, is everybody with me in this example? Okay, let me ask this way. Who is not with me? Should I explain again this whole concept of MapReduce? And this code is fictitious completely, you know. I've tried to keep it a pseudo code. If it is not clear, I can explain again because this is most important thing. All right, all right. So this was how you basically used Hadoop to solve your problem. Here we just counted the words in the input, okay, using MapReduce. Now take the case of next one. All right, same again, the same one in a different sort of visualization is here. Okay, so here I have just demonstrated with a single map. Okay, now imagine that your file is located on multiple machine. Imagine that your input file, some portion is on one machine, some portion is on another machine. Sa re sa ga, sa re sa, right? Node 1 contains this text, node 2 contains this text. Okay, this is just for example reasons, otherwise this input will be in GBs, not bytes. All right, so the same function will be called here as well as here. Node 1 and node 2 both will execute same function of yours, and your input is going to get sorted here as well as here, and then merge and shuffle will happen. So Sare Saga will become Sa1, Re1, Sa1 and Ga1. Here also Sa1, Re1 and Sa1. And once the merge happen, merge and shuffle means, so first this gets sorted by on the same machine. This also gets sorted on the same machine. Once once that happens, it get merged together in the fourth step. You can see that it has got merged in the fourth step. And in the fifth one, where your reduce is being called on each of the keys, your reduce converted into the output. Okay? Is everyone with me? Excellent. Excellent. So yeah, reduce also happens on node, but right now in this example, reduce happens on only, seems to have only one node, but it can happen on multiple node also. So that is a very difficult question to answer. Which node does reduce happen, right? So generally, reduce happens only a node which is free and which is closer to node 1 and node 2 both. Okay. S- Yeah, reduce and merge shuffle happen on the same node. All right. How much will be difference if same solution is applied to Unix? Mm, see, we used the same approach in case of Unix, right? Let me think about it. What exactly your question is? How much will be difference? See, the biggest difference we had was in transporting the data to node 1 and node 2. Here the data is already there. As we talked about HDFS, node 1 node 2 already had those blocks, right? So that will be the biggest difference. Say for transferring around few terabytes of data across the in your cluster takes couple of hours. Abhishek? Yes. So the code is, there's the concept here that code is being sent to the data, and you see the map is being run on node 1, same function again on another one. So yeah, great. So I'm happy that we are able to understand that the code is being sent to the data. All right. Now next step. Now here there was only single mapper for you. Here they become two maps if your data was lying on two. And the next one is you have got two reduces. Okay. You have got two reduces. All right. Now, in case of the fourth step, in this fourth step, what is happening is the keys will get shuffled. Okay, like after 3, ray is existing on both sides as well as psi is existing on both sides, and after a you know little bit of shuffling, it will be figured out that should sa be sent on the left hand side or ray be sent on the right hand side, right? So so based on certain computation, based on certain statistics on which side keys are more, on which side of the, whether this contains the keys more or the other one, the transfer will happen. As a result of fourth, as a result of fourth, the sa is going to go on to the right hand side of the leg, and ray is coming to the left hand side. More important here is that keys are getting transported, keys are getting shuffled, okay, so that it is always guaranteed that the values for a particular key always get processed at a single time. Meaning, when we say run a reduce function on all values of a key, that sentence should remain valid. It should not happen that half of the values of a key are executed once and half of the values of a key executed in the next pass of a reduce. Okay, so every time a reduce function gets executed for a key, all the values for that key should be there. Okay, and that can only happen if shuffling of keys happen between the nodes. S- to reduce, yes. No, I did not get your question. So no, result 1 will be stored on two different nodes, right? I need to understand that question again, Sanjay. I'm not able to get it. All right. If you could reword it, it'll be great. So this is how the map reduce concept works. Now, as a result, you will see two files generally. Here it seems like a one, but if you have multiple reduces, in case of your MapReduce, there'll be two separate files created in HDFS. So reduce puts all node 1, node 2 read from the HDFS, and reduce after finishes it writes back to the HDFS. Okay. While this intermediate data like here and here is on the same node, is on the local node. All right. Now the other way you can think about MapReduce is in terms of your SQL. Okay. In terms of SQL, as in when we say group by clause in SQL, what does it look like? Group by clause has two parts. One is aggregation, other is grouping by something. Okay, grouping by something. So when we say group by something, that something is, that group, decision of something is what map does. So your map basically tells by the way of giving output that this is the key on which my data needs to be grouped by. Okay, and the reduce is basically like your aggregation function for each of the group of key, how to convert it into singular value, each all of the values, how to convert into a single value for that particular key. That is what a reduce is about. Okay, so this is quite analogous to your group by. Okay, this analogy is clear to all of us. I like to repeat it if you want. Okay, so this one here, when we said map, right? Map gave key value pairs. Why did it give key value pairs? So that Hadoop can sort your data based on this key. And then Hadoop will form these groups, key and values. Values are array of value. And array of value, the value, the one which your map is spitted out. Your map is spitted out key and value. Hadoop took all those values and then grouped by the key and formed array of values. And reduce function is like your aggregation, like count stars, sum, average, and average and mean deviation or whatnot, right? So reduce function is more like your aggregation function of your SQL, right? So that's how you can take analogy. You can think of the way when you think used to think about group by clause. Similarly, you can think about whenever I do group by, the my my table gets grouped by that particular value, and we get values, and on those values we can apply an aggregation, right? Great. So here is some assignment for you. I have kept difficult assignments for you. Then the So any questions as of now before I move on to the assignment? So sample code for reduce was very small, and, and actually this is good enough. If you look at it, it says function reduce word and frequency array and array dot sum. In case you are looking for specifically for Java, can you please go to a machine and show a sample code and how is it executed? I think I have written some map reduces and I need to just see. And I think you can actually, so I'll show you some of the code which I wrote for. So for example, there is this multiplying a matrix. It's a little more complex than you would imagine. I wrote it few days back. Okay, so I think I would better pick up something simpler. So when I was executing this code here, okay, Hadoop, okay, so let me just go back to the first screen. Okay, so in this case, let me just pick it up. And this one. So we have Hadoop jar, and this is the one which contains the same code which have been explained just now. Okay, the explanation which we have just now given for the code here contain, this one contains those examples. Okay, and here basically we are saying Hadoop is the client. We are telling it to execute our jar this is the jar which contains our code. Jar means a bundle of code. Okay. And we are telling this jar that execute this particular algorithm out of the whole list. Okay. So you want to see the content of the jar. Okay. And instead, I'll show you here. Okay. Don't get uh, tensed. I'll show you this here. This will be better. So this is my mapper. Okay. This is my mapper. You can see the mapper. I was given a text and I splitted the text by tab and space. I also removed anything non-alphabetic and numeric and then converted it into lowercase. Okay. Basically, I am making my word clean. Okay. So I took the text line by line. My map will be called line by line. All I did here was replaced space and tab with uh, splitted my input text based on space and tab and then removed non-alphabetic characters and then converted into lowercase and printed that word and numeric 1. Okay, this is equivalent to saying I'm printing my word space 1. My word is the value and 1 is my word is the key and the value is 1. Long writable 1, do you see the 1? Okay. And then in the reducer, if you see the reducer, this is my reducer. This reducer is very simple. I iterated over all the values. For each of the value, increase add to the sum each value to the sum. Okay, go over each value and add it to the sum. Sum is initially 0. Okay, so that's what reduce does, and all it does is it prints out back the key and the summation. Ram and Manish, are you okay? Is the font visible? All right, all right. So, and the when you execute this, something like this happens. And while executing, we are telling that this is my input folder, this is my input folder, and this is my output folder, right? So, and then we execute it. So let's see what error are we getting. It's saying output directory already exists. Okay, let's just, whenever you get this output directory, that means you need to either delete the directory or create a new one. So output is always written to a directory. Okay, it requires that it requires a fresh directory on which it will be creating the output. So you can see that it is executing MapReduce, and in the meantime, it has given a URL because it's sort of a batch processing. It has given you a nice URL to track the progress of your job. So it says that word count is running. All right. So this shows you the progress of your job. Anything you do, whether you are writing your SQL in Hive or you are doing Pig Latin, everywhere the same MapReduce will get executed, whether through Java or anything. Okay, so it's doing all of that. It is will also show you the detailed statistics at the end of the process. Okay, it shows you that how many shuffled groups were there, what happens, and all of these details it will show you. Okay, so will the data from SQL, okay, all right. Yes. So Abhishek, right now I have just demonstrated for quick reasons the Java part. Next session we'll be talking something about MapReduce using streaming process, where you can use any programming language you wish to do, and for the MapReduce. Okay. any programming language you wish, you can use it in MapReduce. Okay. Okay, we have got some more question. I have an already existing database, say SQL, and if I have to set up Hadoop, okay, if you have an already existing database, say SQL, okay, and if I have to set up Hadoop and read the SQL database, how do I do? Very good question. So there are specific tools to do that. Also, inside your MapReduce, the way we have demonstrated, you can write the code to connect to the SQL server. Okay, but in case your mappers are many, and there are chances that you will be hitting the database too badly. So there are many tools which help you do the importing from, such as Scoop. We'll be talking about a tool called Scoop, which basically takes the data back and forth between MySQL or any JDBC supported database to HBase or HDFS or Hive. Okay, so I said back and forth, so which means that you can take your data from MySQL, put it onto HDFS, start processing through Hive or MapReduce, and once you are done with that, you can again pull that data back into your MySQL. Can we use Visual Basic or Lotus script to perform MapReduce? Yes and no, provided your programs give out keys and values, then you can use them. Any system command which can give key value pairs can be used via streaming process. All right, we'll show you with a binary the Unix using Unix commands with these. Okay, all right, so now let's go back to the problem definitions. So this is some assignment for till before the next session. Okay, and before attempting this, please finish the quizzes are easier for to get warm up. Okay, if you haven't finished the quizzes yet, work upon the quizzes, and once you're done with the quizzes, yeah, I'll make the jars available. That those jars are will be available after the session number 3. Okay, session number 4 actually, but let me just try to open it up for all. Okay, so under the session number 4, that jar will be visible to you. Okay, Manish, it'll be a big zip file containing all the libraries and all the source code. Okay, in the session number 4, I'll make that available. Now, let me describe these 4 problems which I want to discuss. And here, first question to you is, if you, instead of counting the frequencies of the words, if you had to count frequencies of the letters, do you still need MapReduce? You have to write it down a big text format. Okay. And right now you can just write it in an email and respond to me. In the meantime, we are also experimenting on something like online editors so that you can write then and there inside our learning management system. Okay. Second one is find anagrams in a huge text. Okay. A best approach to answer these questions would be maybe something like a Google Docs, okay, in which we can have the discussion line by line on your approach. Okay, and you can write in plain text or pseudocode or actual code, whatever you wish to do. Okay, even a theory paragraph will be good enough, and if you are good at coding, you can write the actual code. Okay, and let me have a look. Pseudocode is also okay, and paragraphs are also okay, and a combination of all three is also okay. Here the focus is on converting any problem into maps and reduces. So first question was how to do the computation of frequencies, and do you need map reduce to do it? Will it be great if we do it locally? Will it be great if we do it in a normal fashion or using map reduce? Right, now second question is, you are given huge text. Okay, and you have to find anagrams in this text. And what is anagram? Anagram is the various permutations of the letters. If you twist a word, you will form an anagram. So if you take cat and you twist it a bit and it becomes act, act is an anagram of cat, and cat is an anagram of act. Okay, TAC is also anagram of cat and act. So given a huge text, you have to bring the anagrams together. You have to say that these are the anagrams. Okay, you have to bring the anagrams together. That is the objective of this exercise. And how would you do it? Using MapReduce. No, anagram, each anagram doesn't have to have the meaning in this case. Thank you for making that one. I'll just put it up here. And anagram. Generally in anagrams problems, anagram has to have the meaning. Does not need to be to have a meaning. Good. Right. So all right. So we have this. Now, how do you do it? First, you try to do it your normal way, and then try to think in terms of how can you bring anagrams together? What key should be formed such that on all anagrams become the values of that particular key, so that all anagrams come together. All right, that is second problem. Third problem is, yes, it is similar to jumbling the letters. Okay, so okay, say art, rat, tar, and what else? Tra, and what else could be there? RTA, okay, and ATR. Am I missing something? For these are all the anagram possible with ART. All right. So you have to figure out the anagrams in a given huge corpus of text. Okay. Now, third question, why we are actually talking about these kind of questions is so that you get the clarity of when to use MapReduce. Okay. So all we want is as a end result of this exercise is just tell me what should be the key and what should be the value and what should go into your reduce. That's all. Now you got a huge DNA sequence of people. Okay, you got the DNA sequences of the people across the world. You have to find out all the people with same DNA. So for example, user 1 has got ACGT, user 2 has got TGCA, and user 3 has got ACG. Now if you see, user 1 and user 4 both have got ACGT, therefore user 1 and user 4 need to be brought together. Okay, so you have to list down in this format that user 1 comma user 4, user 2, and user 3 comma user 5, because they have the same DNA sequences. Had it been a SQL table, you will simply say group by second column and concatenate the first values, right? Make sense? So that is third A. Now let's have a look at third B. So third B is essentially a little twisted version of third A. It says that some scientists said that people with either identical DNA or exact reverse DNA they belong to the same family. Now you have to find out such people who belong to the same family. Like for example, ACGT and TGCA as well as ACGT, they should be brought together. User 1, user 2 and user 4, because user 1 and user 2 are ide- e- exact mirror images, and user 1 and user 4 are identical. So all the people who have either identical DNA or complete reverse of it, a mirror image of it, complete, if you read it from the right to left, it should be the same. It would be same as your word, right? So like ACGT is a mirror image of TGCA. If you read it from right to left, it becomes ACGT. Therefore, user 1, user 2 belong to the same family. Now you are given this huge corpus of huge list of such DNA and people, and you need to bring the people from the same family together. That is the objective of this exercise. So think about it. It is not really a big deal. Okay, just you just have to tell what will your map do and what will your reduce do, even without code, even in a paragraph of lines, that will do. All right. Now the fourth problem is a bit tricky. In this democracy, not everybody is equal. There is a country in which democracy, the person who has the bigger bank balance has got, his vote has got more power. Okay, now people are voting for each other and you have to find out who has got maximum vote. Okay, so as an input you are given bank accounts of bank account information of all the people and voting details of the country, like who voted for who, as well as you got the list of who has got how much bank account. Now based on this you need to tell who has who has got how many votes, and the way the votes is counted is based on the bank accounts of all the voters for you. So if a, two persons voted for me, say for example in this case F is voted by C and C has got a value of 11, so F's vote count is 11, and V B and C is voted by A and B, and A and B, 5 plus 1 means 6. A has got a wealth of 5, B has got a worth of 1. The summation of A and B is what C gets as a vote count, because both A and B has voted for C, right? So now given this huge list, these two huge lists, how would you compute the vote count of all the people? All right, these are the four problems I want you to work upon tomorrow. All right, is everybody with me? So let's meet next weekend again the same time. For the people from US it will be Friday and Saturday evening, and for people in India it will be Saturday and Sunday morning. Okay. All right, is yes, presentations will be presentations, recordings and problems all will be available in the LMS. Okay, so finish your quiz of first session and finish these assignments, and that should be good enough. Yes, Spencer, I was in the middle of session, that's why I could not reply to your answer. Okay, that's another good question. So, does every problem have to have a reduce? Answer is no. Okay, answer is no. Yeah. So, not every problem need to have a reduce. Thank you for that question. I missed that part. All right. So, feel free to get back and ask questions if you have more, and just also be active on our forum. We have just launched a forum. Okay, we have just launched a forum here. Okay, so please do it before the next session so that we have something to discuss more about this. No, you don't need any programming language for this. It is completely up to you in whatever you feel more comfortable. Whether you feel in Java, you feel in Python, you feel in pseudocode, or you feel good about writing plain text, in plain English. Everything is fine. All right? But make sure that you work upon it. All right? And be active on this forum. You can ask questions here also. All right then. Have a good day. Okay. Does ETL tools support reduce? Mm, I mean, how should I say? Mm, which ETL tool are you talking about? Oh, that I don't know actually. That I don't know. But it's a great concept to have. Okay. If you want to get gross margin for a country, say US, can you give an example of how that will be stored? Okay, okay, okay. This so I'll like to answer it in detail, Shilpa. So can you just write it down on the forum? I'll actually give it for all the people. This will be a good example to do. Okay, here on the forum, just write it down with a simple example, and I'll answer it there with the details. All right. I'll so that I can right now I'll be just talking and not giving the proper example. All right. So let me try to answer it in a proper fashion. Okay, great. Yes, yes, yes. Okay, great. It was a great session. Thank you all, and you all have a great day. Bye bye. Have a great day. Thank you all.